to the second session of this morning. I have great pleasure to introduce you to Professor Carlos Alves from the Department of Mathematics at the Lisbon Institute of Technology, Instituto Superior Técnico. And Professor Carlos Alves, we have a long-time cooperation project with him and also with Marcelo and on this topic of the reciprocity functional and its application for the solution of inverse problems. So, please, Carlos, it's a great pleasure to have you here. Please have the floor.
So, thank you very much, Elsie. I would like to first thank the organizers for the invitation. It's a pleasure to be here and to be in IMPA with all these people interested in inverse problems, both from the engineering point of view and from the mathematical point of view. Well, I come from the Department of Mathematics, but I started a long collaboration with the Department of Engineers, the Mechanical Engineering Department, with Elsie Orlande and Marcelo Colaco, and also the Department of Nuclear Engineer with Nilsson Roberti. So I'm going to talk about some of the work that was made by us, basically considering this technique of the reciprocity functional to the application of to the solution, basically the numerical solution of some inverse problems. So I will start first with some work made with Nilsson Roberti and together with Nuno Martins and Robert Mahmoud. So this will basically consider on the detection of a characteristic source. This is perhaps the first known inverse problem in the literature, since it has been recorded from the 30s, the work of Novikov, which was an inverse gravimetry problem, which consisted on detecting the shape of a gravitical source. Well, here we consider this taking into account the measurements on a certain boundary, but of course this can be seen as either as an artificial boundary or not outside the domain. And usually in the gravimetry problem, we consider not the Helmholtz equation, but we consider only the Laplace equation. So basically, the idea is to get from the knowledge on the boundary, so from the input data or measurements, or both at the same time can be seen as measurements. This depends on the type of physical problem that we are considering. We wanted to know this parameter, which is in fact the characteristic source that lies inside the domain. So despite this being a very ancient problem, not a full solution has been completely known about for instance, the uniqueness of solution. So the inverse problem consists, of course, in getting this from the unknown, as I told you. And as I told you, when lambda equals 0, this is an inverse gravimetry problem. Of course, the idea here is to introduce this reciprocity functional, which we may understand as being only the application of the second Green's formula. But as a structure in itself has some knowledge that will be important in the following. For instance, so we define this from the measurements that we have on the boundary. So we introduce a test function. I'm not putting here mathematical spaces, but this can be defined, for instance, for instance, in the Sobolev space H10. And we have the knowledge of the normal derivative and the knowledge of the field on some boundary gamma. So these are both G's are known from the measurements. Now the test functions that we consider can be of different types. If you consider the case of the Laplace equation, usually you will take just harmonic test functions, meaning that this lambda will be equal to 0. But as we here are considering the Helmholtz equation, what is most appropriate in this case is to consider the reciprocity functional with the v-test functions verifying also the same Helmholtz equation. So what comes rather simply, and this is an observation that comes back from Calderon lectures in IMPA also in the 80s, is that by using this sort of strategy, you will get just the integration because you are dealing with a characteristic function. So this delta u term will just be equal to the, together with this part, which is the characteristic function, will just remain to the integration of this test function on the small set omega. For instance, in this case, we may use plane waves, which are solutions of this, which are full solutions of these waves, for the case that lambda is not null. So with unitary directions, we can just consider a sort of frequency here, which is related to the square root of minus lambda. And of course, if lambda is null, we may use complex monomials. And this is this was the usual situation where you could consider complex monomials. And in fact, if you consider this as complex monomials, this raises also an interesting question in terms of complex variables, which is to know if a function can be determined from the integrals in the complex variables. So, for instance, the domain omega, you will know the value from all the integration from complex monomials. So you can consider this to be the integration of any harmonic function, any complex harmonic function. You know the value, and you want to try to determine from the value of the integrals where what is the domain omega that produces this sort of moment measurement. So in the case of the Laplace equation, this is very simple because we will get the barycenter just by considering two types of functions, which are in this case the first degree polynomials. So you will just get this from this simple measure. And in the Helmholtz equation, as we don't have polynomials as test functions, we can only rely on these plane waves as the test functions. Of course, we can consider other type of test functions, but these are the simplest ones which we can use as test functions to compute the integrations in this case. So in the case of a symmetrical shape, we can get the barycenter formula exactly in the same way, and this is given by a simple formula that you can deduce, which comes from the logarithm of the ratio between the two directions which are opposite. So we are basically considering two opposite directions as test functions, so this does not require a sort of an observation. This is just a requirement on the test function, so we may choose them. And by just calculating the reciprocity functional on the boundary, we get these integrations on the full unknown domain omega, and this will lead us to the barycenter formula. In the case where the domain is not symmetrical, we can use this formula also to detect an inner point for a convex obstacle, but this will no longer be the barycenter. But this can be related to some information inside the domain. So, for instance, by just using some computation using this formula, you can get quite precise values. So this is just a simple numerical calculation here, where you can find that even with a considerable amount of noise, you can get the barycenter calculated quite well. The position error is very small, even with a high number of, with a high increase of noise. Notice that the reciprocity functional has also a property, because since you are integrating all over the boundary, this means that you are not taking the data on its own. You are integrating it, so you are sort of regularizing its values. So you take that into account. It's a sort of regularization incorporated in the reciprocity functional. It's a sort of weak procedure to get the knowledge of the functions and its values. But this works very well in terms of the detection of the barycenter or a similar one. But now I would like to present you this example which was presented in 1978, and this is Sakai counterexample, which is a counterexample for uniqueness that exists for the harmonic shapes, meaning for the shapes that you have in an harmonic environment. So the idea is that you know from Novikov you know that it was possible to get the uniqueness for any star-shaped function with respect to the barycenter. So if you had a function defining the radius, and you take a star-shaped function, you knew that this would only be possible with a single measurement on the boundary, and so a single or multiple in this case will be the same. But in 1978, and in fact Sakai proved this in the context of complex analysis. He did not consider the inverse problem for the gravimetry problem. He just presented the uniqueness counterexample, which is basically a clever way of using something that was already known, which was that if you had an hole in your obstacle, so if the characteristic function was something like this, this would be related with another shape which was with the same, basically with the same volume, but made inside. So he basically considered two, and he took some parts and put others just to get the picture nicer, I guess, and also to the purpose of having a convex, a connected set. not convex. It's a connected set. And you have these two shapes, the red one and the blue one, which are completely, which are different. It's a sort of symmetry, but in fact they produce, they will give zero null field. The difference between the two solutions will give a zero null field between outside this domain that is defined by the two shapes. So you are not able to find a uniqueness, for instance, for connected sets. And it's still an open problem to know exactly what sort of sets you can guess. The best guess is still the Novikov guess from, at least from my knowledge. I would like to know more about this if you have any other information concerning this. But the best knowledge that I know is that the star shape is uniquely defined by the star shapes with respect to the barycenter. So this sort of counterexample makes things pretty hard if you want to guess a better estimate in this situation. Now, the idea to do the approach for the inverse problem in the numerical terms was basically to consider from the information that you have from the boundary equivalent transmission problem. So basically you construct an equivalent transmission problems, and you use for instance, in this case, we use the Levenberg-Macquardt algorithm together with the reciprocity functional, which led to a system, well, it's a sort of a system of this type in the context of applying the method of fundamental solutions to the solution of this problem. And we were able to guess the shape using this minimization procedure on the reciprocity functional. So instead of using the minimization on the fitness of the solution to the boundary data, we use the boundary data already, let's say, adapted and regularized with the reciprocity functional. And this gave pretty good results in this situation. So, for instance, this was done with the method of fundamental solutions, and we obtained a sort of a good convergence even for different frequencies. So these were just numerical results that we obtained with this, and it was even robust to relative noise. You can get here, for instance, this was with a sort of even 30% relative noise that we got this sort of reconstructions. So this was one of the issues where you can use this sort of reciprocity functional, and but you can also take other approaches. For instance, to get a first knowledge of the position of the source, we can try to fully get the equation. So if you are just trying to get this, thinking of this as an f, you can try to define parameters which you don't know which one are the parameters. In this case, it is not for the Laplace. It was not for the Laplace for the Helmholtz equation. It was just for the Laplace. But in this situation, the idea would be to create this source term as a function to fit the boundary data just from coefficients that you don't know and you can define in a domain method of fundamental solutions. So in this situation, for instance, if you have a sort of a class of each sources in, let's suppose that the each source is something like this, and the exact source in this case would be a shape like this, you would get an approximation with 10% noise. You could get a sort of reconstruction in these terms. Of course, the problem about this type of methods is that when you try to get the reconstruction from the whole point of view, you are losing accuracy in terms of the jumps. And so this happens that we are able to define the location, but not exactly the shape of the sources when you go to characteristic sources. So if the source is regular, then it's a different problem than if you have an object, if you have a source that is defined by characteristic functions. In this case, the only thing that we were able to find were just the position, the location of the sources, and not a very good approximation of the shapes. Now I'm going to talk about another problem where we used this reciprocity functional, which was in the heat detection of crack conductivity. So this was a work that was carried with Marcelo Colaco, Elcio Orlande, and Luis Abreu, and also with Fabio Bozzoli and Andrea Moscerino. So the scheme of the problem, first I will consider a problem that was mainly developed first with Marcelo Colaco and Luis Abreu, which carried the numeric, not only the numerical experience, but also the experiments. So the idea was pretty simple. This seems like a linear problem, but it's not a linear problem, where you impose and know the data from just one part of the boundary, and then you have an unknown part where you have contact features. And this is, so in the steady state case, this is just the Laplace equation in both parts. And you have a transmission conditions on this inner boundary, gamma, where you have an unknown parameter, which is the thermal contact conductance. And so you are supposed to find out from the knowledge on the upper boundary, from the data on the upper boundary, you are about to get what is this thermal contact conductance. And so the application of the reciprocity follows along the same line. So you have this relation, which is the green formula relation, which gives you this difference between the normal derivatives on the surface together with the Laplacians in a volume aspect. And the application in our problem was to consider these three parts, which basically gave easy relations between these, which the full scheme is basically here. You can get auxiliary problem. Now you define auxiliary problems. You have to, in this case, to define two auxiliary problems. One which is just on the upper domain omega 1, and the other. So in this case, you have basically two possibilities. You can either consider a Cauchy problem, or you can define the functions on gamma 0, and then obtain a sort of basis on gamma. And from this, from simple algebra, we given to this sort of impositions that we make on the auxiliary problems, we are able to get informations on the normal, for instance, in this case, on the normal derivative with respect to some bases. These bases here are defined, in this case, on gamma, but you can also define the bases on gamma 0 and then derive the traces on gamma. So these are two alternative procedures. And a second auxiliary problem, because this had to do with two regions, so that there was a problem which took care of region omega 1, and then there was a problem that took care of region omega 2 together with omega 1, but basically allowed to solve the whole thing in once. So in this second auxiliary problem, basically the situation was the same. We had also a transmission condition here needed to be solved. And we had these auxiliary problems to be pre-solved. Let me just tell you that these parts allow a simplification that will basically get conditions on the reciprocity functionals. Again, with simple algebra, you can get that the difference between the U1 and U2 solution, which in fact will allow to get the parameter H, is basically a combination given by these basis functions that you define. And the coefficients are basically given by this reciprocity gap functionals. And this is quite useful because you don't need much. The only thing that will basically will be needed to get the parameter would be the calculation of these reciprocity functionals. Of course, this is a mathematical derivation. You just have to assume that you are in Hilbert spaces and that's a separable space, and then you can get along with this sort of arguments. So you have both the normal derivative and the jump between the two solutions given by these reciprocity functionals, which are coefficients for some basis beta. And now this reciprocity functional, which is written just by the calculation on gamma 0, let me tell you one thing, because sometimes people ask about this, which is you can have the situation where your measurements are not, so you have gamma, and your measurements are, for instance, well, in this situation, we were just considering some gamma 0 here. But you can even think about the whole thing, the whole domain, and you could not have information on some other part. But due to the fact that if you have the Holmgren theorem working, and if you get, let's say, information in some part of the boundary, you can complete the information just by using of course, it's unstable, and it can give you bad results numerically, but theoretically, you can complete the external boundary just by extending the solution inside. So in this situation, we got this theorem, which basically could allow to give an explicit expression of this thermal contact conductance, which was related here just as the the ratio between two coefficients. The advantages concerning this is that you can pre-process the test functions using the auxiliary problems. You can calculate separately these two terms. Sometimes just the difference between the solutions would be enough for an engineering purpose. Well, you can also derive some estimates concerning the behavior of these solutions. And using, for instance, Fourier or trigonometric basis, we saw that, well, some sort of instabilities start to occur for, let's say, more than 10 terms. So if you consider the expansion in these terms greater, so the expansion that is given here in this sum on J, if this expansion is greater, for instance, if we were taking more than 10 terms, this was ill-posed in terms of these Cauchy problems. There are some, in some simple geometries, for instance, when you consider just a rectangular shapes like the ones that are produced here, you can calculate explicitly the solutions, and some of these problems are mitigated by the fact that you have the full solution, so you don't need to solve a numerical analytical a numerical solution for the auxiliary problems that can lead you to extra numerical errors that produce also some noise. For instance, this is just the numerical simulations that we got from the first works that were made. So we were able to get more or less good results for, let's say, again, this is a sort of problem that you have here, is the fact that since you are trying to approximate functions that are not necessarily regular, you may get a sort of Gibbs effect as you have when you have the Fourier approximation of non-regular functions. So in this case, we got pretty good results, even in some, in this case, with not too much noise, but with 1% noise, the results were quite acceptable from the experimental point of view. So we even did experimental simulations. This apparatus was made by Luís Abreu, and we tried to get this defect on the material, which was a small plaque of with this depth and a length that was, let's say, more or less constant, just because we did this first in 2D. And the results that we obtained were more or less okay, taking into account the fact that this predicted exactly the smaller values of the parameter, exactly where the defect was placed. So this was quite a concordance between the experimental and the numerical and the theoretical point of view. Again, we also did other simulations concerning what happens in now the framework. It's a little different, but you can see this as a sort of, so we were considering basically omega 0 and or omega 1 and omega 2 here, and this would, and the unknown part was this gamma here, and so basically we're extending this practice to this sort of situation where the gamma would be the full unknown boundary here. And the idea in this case was basically the same. Of course, this is not, this is well known that you can get information in this sort of situation. And again, we tried this with a sort of artificial problem that allowed to define the basis for this type of function. So, so in this situation, what we got was that the detection of conductivity, so in this part of the inner boundary, could be used taking into account the relation between the reciprocity functional, and also in this case we consider not, so this is written here, this was not just the Laplace equation, we had some heat terms, so that's the reason why it appears here, this heat term, but using an induced basis which was generated by functions that were solution of the auxiliary problems, of these auxiliary problems, we induced the basis just by putting some different functions phi and then measuring it on the gamma interior. We were able to get the inner flux given by a sum of these inner products, which were, this is basically related to the reciprocity functional together with the heat source. And of course, this produced the results more or less as good as before. We still have this problem of fitting up discontinuities. So as you see here, there is this discontinuity of the jump, and we are still trying to manage to get the best fitness of this parameter. But of course, if we know where the jump is, of course, that would be more simple to do. But assuming that we don't know where the jump is, we are trying to get a better way to find this sort of problems. So this is basically what I would have to present you. Thank you.